So in our previous session we had studied some basic concepts of sets, that is what is the definition of sets and what is the union of sets, intersection of sets, complement of sets. These all were the things we have studied in our previous session. Today let us proceed a little further, that is today let us begin with the indexed family of sets. So how we are going to define the index family of sets? What we are going to consider is, let us consider a non-empty set A. Then for each lambda belongs to this index set, we will be given a set A lambda in such a way that A lambda, where this lambda belongs to this indexed set, is the family of sets indexed by the set A. So how we are going to define it? We are going to write it as, here the set A, this is the indexed family of sets. This is defined as A lambda, where this lambda belongs to this indexed set. Here this lambda is called as an index and this is called as an indexed set. So for considering a non-empty set A, this A here is as said indexed family defined as A lambda, such that lambda is going to belong to this indexed set. So soon after this index set, let us proceed with the arbitrary union and intersection of sets. See, arbitrary union of sets, how we are going to define that? Here let A lambda belongs to this indexed set, be any arbitrary family of sets. Then union or arbitrary union of sets, we are going to denote it by union of A lambda belongs to this indexed set. It is how it is read, union of A lambda for lambda belongs to the indexed set, and it is going to be defined as union of A lambda belongs to indexed set. This is defined as, this will be equal to x. What is x or how is x? It is such that x belongs to A lambda for at least one lambda belongs to the index set, means for at least one of the lambda belonging to the indexed set. This is how we are going to define with the arbitrary union of sets. The same way now let us define with the arbitrary intersection of the sets. So we had studied about this arbitrary union. Now arbitrary intersection. What it is going to be again? Let A lambda, where lambda belongs to this indexed family of set, that we are going to say that intersection of arbitrary union of sets. And how we are going to denote it? We are denoting it as intersection of A lambda belongs to this indexed set, and we are going to define it as x, such that x belongs to A lambda for every lambda belongs to the indexed set. See, in the arbitrary union we had said that for at least one lambda belongs to this indexed set, whereas now for the arbitrary intersection it is that for every lambda should belong to this indexed set. Now let us continue with generalized De Morgan's law. So we are going to start with the generalized De Morgan's law. That is, we have two generalized De Morgan's law. One is for the union and the other is for the intersection. So let us now prove this generalized De Morgan's law. Okay, how we are going to write it? For any indexed set, it is again for indexed sets. Generalized De Morgan's law, that is for any indexed set, that is if A lambda belongs to the indexed set, that is if A lambda, this lambda belongs to the indexed family, that is be the indexed set, then what we are going to consider? Then union of, then we have two laws, that is first one is union of A lambda belongs to this indexed family. Its complement is equals to intersection of A lambda complement where this lambda belongs to this indexed set. This is one of the law, and the other is that intersection of A lambda, that is intersection of A lambda where lambda belongs to this indexed set, its complement is equals to union of A lambda complement where lambda belongs to this indexed set. Now what we will do, one by one we shall prove this. That is, let us first consider for union of A lambda. Lambda belongs to this indexed family, its complement is equals to intersection of A lambda. Lambda belongs to the indexed set. So first let us consider that X be any element of union of A lambda, its complement. Let us first consider that. Let X be any element of what? Element of union of A lambda. Lambda belongs to the indexed family, its complement. So how we are going to denote this? We are going to denote this as X belongs to union of A lambda. Lambda belongs to the indexed family, that is union of this complement. So if it is going to belong to this, it simply means that X is not going to belong to the union of A lambda. If it is going to belong to its complement, then it simply means that X does not belongs to the union of A lambda where lambda belongs to this indexed set. If so, what is going to happen? It implies X will not belong to A lambda. If it is not going to belong for union of A lambda, then it is not going to belong for A lambda for any, means for any lambda belongs to this indexed family. So if it is not going to belong for this, then obviously X should belong to its complement. Then we are going to write it as it is going to belong for A lambda complement. If it is not going to belong for A lambda, it is going to belong for its complement for every lambda belongs to the indexed set. So if it is going to belong to this, then obviously it should belong for the intersection of this family. That is, this implies X belongs to the intersection of A lambda complement where lambda belongs to this indexed set. So what first let us consider? We shall consider that intersection of union of A lambda where lambda belongs, union of A lambda, lambda belongs to the indexed set, its complement is subset of intersection of A lambda complement where lambda belongs to the indexed set. Let us consider this as equation 1. So now again we need to prove the other part, that is it has just become the subset. Now what we are going to consider? Again let us consider that X be any element of, let X be any element of intersection of A lambda complement where lambda belongs to this indexed set. We are going to write it as X belongs to intersection of A lambda complement where lambda belongs to the indexed family. If it is so, then what is obvious? It is obvious that X will belong to A lambda complement for every lambda belongs to indexed set. It means that X is going to belong to A lambda complement for every lambda belongs to this indexed set. What does this mean? This means that X will not belong to A lambda, means this means that X will not belong to A lambda for any lambda belongs to this indexed set. If it is so that if x is not belongs to this a lambda, it just means that x is not going to belong for, this implies that x is not going to belong for union of a lambda where lambda belongs to this indexed family. It just means that x belongs to union of a lambda, lambda belongs to the indexed set, its complement. So what does this mean? This means that intersection of a lambda complement where lambda belongs to the indexed set is a subset of union of a lambda, lambda belongs to the indexed set, its complement. Now from equation 1 and equation 2, what does this mean? It means that intersection of a lambda or union of a lambda complement where lambda belongs to the indexed set is equals to intersection of a lambda complement where lambda belongs to this indexed set. Now we just proved the first one, that is, now we proved that union of a lambda where lambda belongs to the index set, its complement is equals to intersection of a lambda complement where lambda belongs to this index set. Now let us prove this second part, that is, let us just keep this and continue the second part. We shall prove the second part of this, that is intersection of a lambda where lambda belongs to this indexed set will be equal to union of a lambda complement. The proof is same as that of the first one. So let us try to prove it. What it is? Intersection of a lambda, lambda belongs to the indexed family, its complement is equals to union of a lambda complement where lambda belongs to the indexed set. So what we shall do is, first let us consider that x be any element of union of a lambda complement. Let x be any element of union of a lambda where lambda belongs to this indexed family to its complement. If so, how we are going to write it? We are going to write it as x belongs to, it is intersection of a lambda complement, intersection of a lambda complement where lambda belongs to the indexed family, means it just says that x belongs to intersection of a lambda, lambda belongs to the indexed family to its complement. It just means that x is not going to belong for, intersection of a lambda where lambda belongs to this indexed set. It means that x is not going to belong for a lambda for what? For some lambda belongs to this indexed family. If x is not going to belong for a lambda, it just means that x is going to belong for, it is for every, it just means that x is going to belong for a lambda for some lambda belongs to this indexed set. If it is going to belong for a lambda, it just implies that x is going to belong for union of a lambda where lambda belongs to the indexed set, that is a complement. X is going to belong for a lambda complement for some lambda belongs to this indexed family. If so, it is going to belong for union of a lambda complement. Means what we proved? We proved that intersection of a lambda, lambda belongs to this indexed set, its complement is a subset of union of a lambda complement where lambda belongs to this indexed set. Now again what we shall consider, again let X belongs to the union of A lambda complement. Again, let X be an element of what? Element of union of A lambda complement, where lambda belongs to this indexed set. It means it is written as X belongs to union of A lambda complement, where lambda belongs to this indexed family. If it is so, it means that X belongs to A lambda complement for every lambda belongs to the indexed set. It means X belongs to A lambda complement for every lambda belongs to this indexed set. What does this mean? This means that X is not going to belong for A lambda. X is not going to belong for A lambda for every lambda belongs to the indexed set. So what is going to happen? If so, it means that X is going to belong for the intersection of, this implies X is not going to belong for intersection of A lambda for every lambda belongs to this indexed set. This means that X is going to belong for the intersection of A lambda, where lambda belongs to indexed family. So its complement. So what we got to know? We got to know that intersection of A lambda, where lambda belongs to the indexed family, or it is that union of A lambda complement, where lambda belongs to this indexed family, is a subset of intersection of A lambda, where lambda belongs to this indexed set, to its complement. So from 1 and 2, what we got to know? From equation 1, this is our equation 1 and this is our equation 2. From this equation 1 and 2, we got to know that intersection of A lambda, where lambda belongs to this indexed family, its complement is equals to union of A lambda complement, where lambda belongs to this index family. Hence we proved the generalized De Morgan's law. So now what we are going to continue with the functions. That is, first we will define functions and then we will go to the image of a function and inverse image of a function. So what is function? We can define function as let x and y be two non-empty sets. What kind of sets they are? They are sets, they are two non-empty sets. A subset F is of the form x cross y is called a function from x to y. How we are going to write? F, it is a function from x to y, or we can also write that it is a function from x to y. And if, when we are going to say if and only if, to call F a function from x to y, it has the condition. What is the condition? If and only if to each x belongs to x, there exists a unique y in y such that x comma y should belong to F. That is, there should exist x in x and y in y such that x comma y should belong to F. It is denoted as F is a function from x to y. And it also follows from the above definition that a relation from x to y is a function from x to y. Means this relation is a function if and only if when it has two conditions. That is, the two conditions are, to each x belongs to x, there exists unique or there exists y belongs to y such that x comma y should belong to F. This condition. And the other is that if x comma y1 and if x comma y2, these both belong to F, then y1 will be equal to y2. See, what does the condition 1 states us? The condition 1 actually states us that in each x belongs to x, F associates an element y in y. Means for every x, f should associate one value in y, and here y1 is equals to y2. The second condition, it states that y is unique. Y is going to, for a given set of x, y is going to be unique. We call C. Suppose I have set x which is equals to 1, 2, 3 and 4, whereas I have a set y which has elements like a, b, c. I am going to define a function from x to y. That is, if I have this as x and if I have this as y, what is going to happen? I will write this as 1, 2, 3, 4 and this is a, b, c. So, f is a function from x to y. So, x with the domain of f. Here, x is called the domain of f and the y is the codomain. So, y is the codomain of f. That is, if it is the domain, y is going to be the codomain of f. The unique element y in y assigned to x belongs to x is called the image of x. Means, if I have assigned it as a, then what is going to happen? What is called the x belongs to x is called the image of x. Here, 1 is going to be the image of a and is denoted by f of x. Also, x is called the pre-image of y. So, now this is going to be called as the pre-image of y. So, what has happened? We have to define a function. There are two conditions. What are those two conditions? That is, for every x belongs to x, there should exist y belongs to y. Means, for each image of x, there should be for each element of x, there should be image in y, and then that is that if x and y1 belongs to f and x and y2 belongs to f, the condition will be that y1 is equals to y2. Means, it is having the unique, that y is always unique. So, now let us study the types of functions. So, the first type of function is one-one function, or we call it as injective function. So, let us now focus on the types of functions. One-one function, onto function, and if a function satisfies both one-one and onto, it is called as a bijective function. So, now first let us know what is one-one function or injective function. That is, we shall begin with types of functions. Types of functions. Among that, first one is going to be what? A one-one function. That is, one-one function, which is also called as injective function. Or before that, okay, we missed the image of a function and inverse image of a function. So, first let us study the image of a function and inverse image of a function. What we are going to write? First, image of a function. How it is defined? It is defined as, if A is a subset of x, then the set f of x, that is, if A is subset of x, then the set f of x. How we are going to define this f of x? F of x such that x belongs to A. F of x such that x belongs to A. What happens here is called the image of A. F of x such that x belongs to A is called the image of A. Means, here where x belongs to A, that is called as the image of A under F, and is denoted by, is called as is called as image of A under F and is denoted by F of A. So how we have defined the image? If A is any subset of X, then F of X will be equal to X belongs to A. Is called the image of A. Is called the image of A under F and is denoted by F of A. Next, now we are going to study about the inverse image of A. This is image of a function. Now we are going to study the inverse image. So how we are going to define the inverse? If this is the image, how we are going to define the inverse of an image? It is defined as if B is a subset of Y, and so what happens if B is a subset of Y, then the set as we have defined here for the image of X, for the inverse image of X, what is going to happen? X belongs to X. It is defined as X belongs to X such that, what is the condition here? Such that F of X should belong to B. Such that F of X is going to belong to B is called the inverse image, is called the inverse image, and we are inverse image under F and is denoted by F inverse of B. Inverse image of B under F and is denoted by F inverse of B.Sc. We studied that if A is going to be a subset of X, then the set, that is F of X such that X belongs to A, is called the image of A under F and is denoted by F of A. The same way inverse image is denoted as if B is subset of Y, then the set F X belongs to X such a way that this F of X should belong to the set B. Then it is called as the inverse image of B under F and is denoted by F inverse of B. Now let us study the types of function. Let us study the types of functions. Types of functions. Among that, first one is 1-1 function, which is also called as injective. We can say that either function is also called as a mapping. We can say that the mapping F is said to be 1-1 if different elements in X have different images in Y. How we can say? We can say that a mapping or a function. A mapping F is said to be 1-1 function if the condition is that if different elements in X have different images in Y. If different elements in X have different images in Y, that is for every element of X there should be a image in Y. Then it is called as a 1-1 function. That is, if here x1 should not be equal to x2, means if what happens, if f of x1 will not be equal to x2, then f of x1 will not be equal to f of x2. This implies x1 will be equal to x2. This is called as like this. If it is going to satisfy this condition, then we are going to say that it is one function, or it is also called as injective function. That is, for different elements of x, there should be different elements in y. Then we are going to call it as a one function or injective function or injection. The other function what we are going to study is onto function. That is, onto function, also called as surjection. What it is? Onto function, which is also called as surjection. That what is going to happen? Let f from x to y be a function such that each element, means let f from x to y be a function, then for each y belongs to y, what is going to happen? For each y belongs to y, or that each element y belongs to y has at least one pre-image under f, has at least one pre-image in f. That is, it should have an element in x. That is pre-image in f. Then what is going to happen? Pre-image under f. Then f is said to be a function from x to y. Then f is said to be a onto function from x to y. It is that f from x to y be a function such a way that for each element y belongs to y should at least have one pre-image in x, one pre-image under f. Then f is said to be a function from x to x onto y, or x onto function from x to y. How we are going to define that? F from x to y is an onto function. That is, f from x to y is an onto function if we are just denoting it, if f of a will be equal to f of a is equals to b. It is also called as surjection. See, for a function to be 1, 1, it should be a mapping in such a way that different elements in x should have different images in y. This is 1 function or injection function or injective. The same way, for an onto function, f from x to y be any function. If for every element of y belongs to y, there should be the pre-image under f. Then we are going to call it a function from x onto y. B, we can also write it as be a function from x onto y, nothing but an onto function. That is, f from x to y is an onto function if f of a will be equal to b. This is also called as a surjection or surjective function. We have another function called bijective function. That is bijective function. How we are going to define this? A function f is said to be bijective. A function that is both injective and surjective. How we are going to define? The function which is both injective and surjective is called a bijective function. That is, a function should be both injective as well as surjective. Then it is called as a bijective function. So next, let us proceed with few of the examples to prove which one that the sets are onto function, one function and bijective. So let us solve a few examples related to it. Okay. We have a question, means they have given us few functions f1, f2, f3 and f4 is also given. That is, what is the given question? Consider the sets x is equals to 1, 2, 3, 4 and y is equals to a, b, c, and they have given us 4 functions. Let f1 is equals to 1 comma a, 2 comma a, 3 comma b, 4 comma c. This is f1. f2 is 1 comma a, 1 comma b, 2 comma a, 3 comma b and 4 comma b. Again function f3 is given. It is as 1 comma b, 2 comma b, 3 comma b, 4 comma c. We have f4 which is equals to 1 comma a, 2 comma b, 3 comma c. We need to show that which one of these function satisfy the condition. That is, what we shall do is, first let us consider for the first one. Solution. What we are supposed to do? Let us consider with the first function first. Each element of x has an image in y under fc. Here x has 1, 2, 3, 4. These elements, that is, we have 1, 2, 3 and 4. That is, each element of x has an image in y under f. Right? Each different element of x has image in y. Let here each element of x has an image in y. Here each element of x has an image in y under f. Of course, we have it. Also, all the ordered pairs in f1 have different first element. Do we have it? First entry is different, right? It is 1 comma a, 1 comma b. So, I repeated 1 comma a twice. 1 comma a, it is correct. For the first one, 1 comma a, 2 comma a, 3 comma b and 4 comma c. Here what has happened? Here all the ordered pairs in f1 have different first entries. See, all the ordered pair has 1, 2, 3, 4. First entries is different. Since all the first entries are different, f1 is a function from x to y. What has happened? All entries of the in f1 ordered pairs, all first entries are different. All first entries are different. Therefore, what has happened? f1 is a function. Now next, therefore what we are going to write? Therefore f1 is a function from x to y. That is, each in this given ordered pair, each first entries have different entries. Therefore, f1 is a function from x to y. Next, range of f1 is set of all second entries of the ordered pairs. That is, how we are going to write range of f1? Range of f1 is set of all second entries of ordered pair. What are the second entries of this ordered pair? It is A, B and C. This is called as the range of f1. So what has happened is, each element of y has a pre-image under this is y, right? So each element of y has a pre-image in x. Do we find? Or we have a pre-image under f. So f1 is onto under f1. Therefore, f1 is onto. See, ordered pairs are different. So each element of y, A also has its pre-image, B also has its pre-image, as well as C also has its pre-image. Therefore, we say that f1 is onto. So how we are going to say? f1 is equals to A and f2 is here. f1 of 1 is A, whereas f1 of 2, this is also is equals to, this is also is equals to A. That is, f1 of 1 is equals to A and f1 of 2 is equals to A. Therefore, what has happened? We were supposed to know that f of x1 and x2, if they are equal, they should be unique. But what has happened here? f1 of 1 is also A, f1 of 2 is also A. So what is going to happen is, 1 is not equal to 2. Of course, 1 is not equal to 2, but f of 1 is equals to f of 2. What has happened? 1 is not equals to 2, but f of 1 is equals to f of 2. Therefore, f is not 1, 1. What has happened? Therefore, f1 is not 1, 1. Therefore, for a function to be bijective, it should be both onto and 1, 1. But here the function is only onto and not 1, 1. What we had considered, each element of x has an image in y under f. So here f1 in this ordered pair, all the first entries were different. That is why we said f1 is a function. Later what we considered the range of f1, which is equals to y. Each element of y has its pre-image in x. Therefore, we said that it is an onto function. But what has happened here is, f1 of 1 is equals to A and also f1 of 2 is equals to A. Therefore, 1 is not equal to 2, but f1 of 1 is equals to f1 of 2. It is not unique. Therefore, f1 is not 1, 1. Hence, it is not a bijective function. So, we proved this for f1, that is function 1. Now, let us same consider that with f2. So, now let us solve the second problem. What it is? They have given f2 is equals to 1 comma A, 1 comma B, 2 comma A, 3 comma B, 4 comma B. So, how we are going to find its solution? Here what has happened is, each element of x has an image in y. Do we have it? Under f2. See, each element of x, 1, 2, 3, 4. Each element of x has an image in y. each element of X has an image in Y under F2. This is obviously that. Next, but the ordered pair 1 comma A and 1 comma B have the same first entry. See here, 1 comma A and 1 comma B, it has the same first entry. But what has happened? But the ordered pair 1 comma A and 1 comma B has same first entry. So what is going to happen if it has the same first entry? F2 does not associate a unique element of Y. If it is going to happen, then what is going to happen? F2 does not associate a unique element in Y. If it is not going to associate an unique element in Y, then what is going to happen? That is, F2 is not a onto function from X to Y. Therefore, F2 is not an onto function from X to Y. Therefore, what has, because its first entries are same, that is why it is not an onto function from X to Y. Let us look for the third one, that is for F3 of 1 comma B, 2 comma B, 3 comma B and 4 comma C. Here we are seeing the conditions of a function. What it is? Each element of X has an image in B. See, each element of X has image in Y under F3. That is 1, 2, 3 and 4. All these elements have its images in Y. That is, it has B and C. So, we said that it has image in Y under F3. Also, all the ordered pair in F3 have different first entry. Also, what has happened? Also, all the entries or also all the ordered pairs, in F3 has different first entries. See here, it is 1, it is 2, it is 3 and it is 4. All the first entries are different. Therefore, F3 is a function from, X to Y. Now we got to know that F3 is a function from X to Y. So, but what is going to happen is range of F3. What is the range of F3? It only has B and C. Range of F3 is equals to range of F3. What are the second elements in F3? It is B and C. For A belongs to Y, we do not find any pre-image in X. For A belongs to Y has no pre-image under F3. Therefore, F3 is not onto. What has happened? For A belongs to Y has no pre-image under F3. Therefore, F3 is not an onto function. What happened? F3 is not an onto function. Now, what about the fourth one? F4, function 4. it has no image in Y under F4. See, in this ordered pair, 4 has no image at all. That is why what is going to happen? If it has no image at all, then F4 is not a function at all, because here 4 has no image only. If it has no image, then it cannot be a function, because we, according to the definition, we know that different elements should have different images. Therefore, here 4 has no image at all, and hence F4 is not going to be a function. Similarly, we have one more example to look after. What is that one more example? Let us consider that we need to prove something, that it is if prove that the function f, prove that the function f from R to R, that is defined by f of x is equals to cos x, is neither 1 1 nor onto, is neither 1 1 nor onto. Cos of x, f of x is equals to cos of x. How we are going to prove that? First, let pi by 3. See, let us, what we consider is, for the proof, plus or minus pi by 3 belongs to the set of R. That is, plus pi by 3. Of course, this is not equal to minus pi by 3. So, we have just considered. Now, but what is going to happen? But f of minus pi by 3, f of minus pi by 3, which is equals to cos of minus pi by 3. This will be again equal to cos pi by 3. Because we know that cos of minus theta or itself is cos theta again. Therefore, cos of minus pi by 3 is again going to be cos pi by 3 itself, which is equals to 1 by 2. Again, for f of pi by 3, it is cos pi by 3, which is again equal to 1 by 2. So, what has happened here? Different elements of the domain have same images. We got to know that f of minus pi by 3 and f of pi by 3 has the same image, that is different elements of domain have same images. If it has the same images, then what is going to happen? Therefore, f2 is not going to be on 1 1. Same images, not an 1 1 function. Therefore, f is not an 1 1 function. It is neither 1 1 nor onto. We proved that it is not a 1 1 function. Now, to prove that it is not an onto function, now let us consider 2 belongs to R. Of course, yes, 2 is going to belong for the R, the codomain of f. R, what it is? The codomain of f. If so, what is going to happen? It is that x be its pre-image under f. Then x be its pre-image under f, that is f of x is equals to 2. What is this going to imply? This is going to imply that cos x is equals to 2, which is not possible or which is absurd. F of x is equals to 2 on re-entry. It is going to be cos x is equals to 2, which is absurd. This is not possible. So, what we got to know? We got to know that there exists no such X belongs to R. There exists an element in the codomain which has no pre-image in under F. That is X. What has happened? There exists an element in codomain which has no pre-image under F. If it is not having any pre-image, therefore what is going to happen? Therefore F is not onto what we considered? We considered that F belongs to the R, the codomain of this function. If so, what is going to happen? X be its pre-image. Then what we proved? If it is a pre-image, then f of x is equals to 2. What is our f of x? F of x is cos x. Cos of x will be equal to 2. This is not possible, which is absurd. It means that there exists an element in codomain which has no pre-image. If it has no pre-image, therefore the function f is not onto. Hence we proved that this function is neither 1 nor onto. We studied about indexed family, arbitrary union and arbitrary intersection, De Morgan's law, function, image, inverse image, and few of the problems related to it. I hope you all are following. Thank you.